Welcome everyone to the tutorial Successful Proposal Writing for Sustainable and Impactful Research from Tenure Track to Endowed Chair. I'm Jeff Mangum from the National Radio Astronomy Observatory. I'm also URSI Commission J Chair, and I'm the moderator for this tutorial. I thought I would start off by just introducing our three panel members. They've all provided a kind of a biographical sketch, which have been posted to Whova, but I thought I would just read those just to give all of our panel members, give you all background as to the experience of our panel members. So first we have Zoya Popovic, who is the Distinguished Professor and Lockheed Martin Endowed Chair of Electrical Engineering at University of Colorado. She obtained her diploma in engineering degree at the University of Belgrade in Serbia and her PhD at Caltech. She's graduated over 60 PhD students and currently advises 15 graduate students in various areas of high frequency electronics and microwave engineering. She's a fellow of IEEE and the recipient of 2 IEEE MTT microwave prizes for best journal papers, the White House NSF Presidential Faculty Fellow Award.
That's enough, Jeff. I didn't think that fit in anyway.
Okay, that's right. It didn't quite fit in with the into the Whova listing, but I did want to point out finally. Zoya's husband is a physicist, but maybe most importantly, 3 daughters. One has a PhD in EE, and all 3, Zoya tells me, all 3 can solder.
Yeah, and 1 can weld.
Yeah, 1 can weld.
Non-EE.
Yeah. Our second panel member is Anna Ferreras, is a senior program officer at the U.S. National Academies of Sciences, Engineering and Medicine, where she manages the U.S. National Committee for Mathematics Instruction, Crystallography Physics, Theoretical and Applied Mechanics, and Radio Science. She's also a consultant, evaluator, speaker, professional developer, researcher, fundraising expert, and advisor for organizational leaders in the private sector, academia, and federal government. And let me just skip down here. Finally, Anna is a winter 2008 Christine, I don't mess up this name, Mirazan. How do you pronounce that, Anna?
Marsayan Fellow. It's a Science and Technology Policy Fellowship that is based at the National Academies. But welcome all. Thank you, Jeff. Yeah.
Okay. Thank you, Anna. And then finally, our third panel member is John Chisum. John is an assistant professor of electrical engineering at the Electrical Engineering Department at the University of Notre Dame, where he currently advises 7 PhD students and 1 undergraduate student in the microwave and millimeter wave circuits and antennas lab. He obtained his PhD in electrical engineering from the University of Colorado at Boulder.
Under Zoya Popovic.
Under Zoya
Not
Popovic.
under.
Yeah.
My students are my bosses.
From 2012 to 2015, he was a member of the technical staff at MIT Lincoln Lab, where his research focused on millimeter wave phased arrays, antennas, and transceiver design for electronic warfare applications. He joined the faculty at Notre Dame in 2015. Let me just skip down here a little bit. John is a senior member of IEEE and a member of the American Physical Society and current vice chair for USNC-URSI Commission D, and that's electronics and photonics. Okay, so those are our 3 panel members. So the way this tutorial will go, each of the panel members will have a presentation. Where I'm told that they'll take questions from participants either during the presentation, but also afterwards. You're welcome to just ask a question if you have it, but also if you would you want to be maybe a little more polite about it, and there's a lot of discussion, you just want to use the raise hand feature in Zoom, I will be paying attention to that. So if you use the raise hand feature, I will hopefully spot you and let you ask a question. So with that, Anna will start with a high-level overview and important advice and hints, especially for NSF proposals. That will, after Anna's presentation, John, as a junior faculty, will give some examples of his successful and maybe even more importantly, not so successful proposals to NSF, DARPA, and the Office of Naval Research. And then finally, Zoya, as a senior faculty, will tell you about experienced average over 30+ years with examples of specific proposals, continuations, and strategies for continued funding. Okay, with that, I'll hand it over to Anna.
All right, thank you, Jeff, for the introductions. Welcome all. I would like to start by mentioning how I start writing proposals. I was very eager during my doctoral program to learn how to do so, because I could notice the difference between the opportunities that were given to me versus other doctoral students who unfortunately were working under the supervision of faculty members that were not that capable of raising a lot of money. So I asked very early during my doctoral experience to my major professor to please teach me and work with me on that type of a skill set. So she started by sharing with me some proposals, by sharing with me the criteria that is often used. And I start reading and ranking and rating the proposals. And soon after then, she started asking me for help on how to draft proposals along with her. Well, soon after I start writing proposals, the magnitude of those proposals expanded, and then I became kind of known in the department as being a good proposal writing. And then I started making additional money by writing proposals for other faculty members. So this is a type of a skill set that is very handy. And it's very handy no matter which sector or industry you're in. There is nothing sadder in this life, I often say, that someone full of amazing ideas that is not able to sell them. Because if you don't have ideas, it's okay. But when you have amazing ideas, but you cannot make them a reality because you don't know how to sell them, that's extremely sad, okay? So we're gonna be working on that today. And when I see excellent proposals, I tend to call them irresistible. You know what, they're irresistible? Because it's like an Einstein idea drafted by Shakespeare. And you look at the record of those kind of proposals, writers and PI, principals and investigators, and they might have many grants and millions of dollars that they are in charge of, but they still do so good that they need to be funded. So I'm gonna go over what I have observed and learned in my experience on proposal writing. So one of the first things is, where do you find money, right? So there are many players out there, you know, and that's one of the beauties of the United States. There is money in many locations. You know, unfortunately, in other countries, they have a Ministry of Science and Innovation. And if you're a scientist and engineer, that's it for you. But in the United States, maybe you have an idea. And if the Department of Defense says, thank you, but I'm not interested in funding, it's okay. You just can tweak it a little bit and maybe adjust it to the space industry, and then, you know, try with NASA. And if they say no, it's fine. You might tweak it to, you know, healthcare application and try NIH, National Institute of Health. So many are government agencies, as I list in the first bullet, US federal and state government agencies like the National Science Foundation, DARPA, Department of Defense, NASA. You also have national laboratories like Sandia Labs and NIST. There are also international organizations, for example, the World Bank, If you are thinking about doing something, for example, with developing countries, it's a perfect place to look for funding. Private sector, there are many companies that actually also give small grants to innovators and investigators. They're philanthropists. They're quite a wealthy man in the United States, so tap on that. And then private foundations like Sloan, Gates. Then you also have professional societies, believe it or not, IEEE, the APS, Antenna Propagation Society, are the ones more connected to your field, but many professional societies also award small grants, especially to early careers. And then finally, NGOs, non-governmental organizations like the one that I work for, the National Academy of Science, Engineering, and Medicine. All right, so how do I find opportunities? Well, one of the first things you need to do is talk to your contacts in your funding agencies. You need to check those researchers also in your field who are well funded. Try to find out where are they getting their money? What are the grants that they currently have? Then also share your ideas with mentors who are leaders in the field. They can give you some tips and hints. They might be aware of a solicitation that is coming up in a few months and you can submit the proposal. Then also investigate who has a similar idea and is already funded. That's another way to find out the money for the idea that you have. Also check companies that produce the equipment that you use in the laboratory. That's another way to go about. Then subscribe to philanthropy newsletters. I get to find a lot of opportunities through those newsletters. And also, please network, network, and network. When you go to receptions, hopefully soon, once we've been vaccinated, I really recommend you to talk and network with others in your field. And last but not least, search, because everything is in Google, right? All right, so how do I start working on a proposal? Well, the first thing, which is the most basic thing, you read the solicitation and you try to figure out if it's a good idea and if it fits. Why I'm saying so? Because many times there are researchers that submit proposals that are just not a good fit for that solicitation or call. You want to send an email to the officer in charge of the grant, introducing yourself, and do not be afraid of ask questions before you start writing the concept paper. You want to organize your ideas. You might need to brainstorm, do a brainstorming exercise just to organize your ideas. Or use a tool. There are many tools out there. Also, I highly recommend you to write a 1 or 2 page concept paper or white paper and share it with that program officer in charge of the funding. Why? Because you don't want to waste your time. Maybe it's just not a good fit for that agency, organization. So why are you going to waste a lot of hours and time putting together a 15 pages a project description? Just organize your ideas and then capture them in a 1 or 2 page concept paper and share with your program officer. Okay, now what are the basic sections in that white paper that you want to focus on? Well, those focus on background. In other words, the problem statement, what are you trying to solve in here? Then what is the goal or goals? What is kind of like the mission? What are you trying to do? Then the objectives, and we'll go over the difference between a goal and objective. An objectives are the steps that you need to take forward in order to accomplish the goal. And then the expected outcomes. What are you trying to get out of this research or idea? Then get the officer's feedback on your idea. He or she will let you know if the idea is a good fit. Otherwise, get a feeling if he or she is willing to fund it or not. You should be able to get a sense after that individual reads your concept paper. Do you think that person is just, oh, well, it's nice, versus, oh, this is a great idea. I highly encourage you to submit a proposal. Then it's giving you the green light, right? So get a sense. Try to read that email or that conversation. When you communicate with the program director, I'm a person that I prefer face-to-face. Now with the pandemic, hey, you need to, I would recommend you Zoom or any kind of virtual meeting, because you want to observe the face of this individual. You want to be able to read if it's in favor or not of funding your proposal or your idea. Try to understand the criteria and the success rate. That is also important, because some solicitations are more competitive than others, and you want to know that ahead of time, right? If you are able to find, and most of the times you are able to find the abstract of previously funded grants under that solicitation, I highly recommend you to look into that. Fellows are not that open about sharing their proposals with others. Why? Because they're considered intellectual property, okay? And so you might find the abstract, you might find a one-page summary, but usually fellas do not post the entire proposal, 15 pages, okay? Now, I highly recommend you to watch webinars offered by the program officer in charge. Many US government agencies do so. They tend to do a few months before is the deadline to submit the proposal. You will learn a lot. Also, it is critically important that the officer understand and support your idea, as I said before, in order to move forward. Also, I want you to be aware that the final decision is in the hands of that program officer, not the panel review, okay? So usually in the review process, all the proposals are collected by a deadline, and then panel reviews are assembled, right? And that's what is considered the peer review. So what happens in those panels? Let me tell you. If you don't like at all a proposal because you think it's extremely bad, in order to rank it as extremely poor, like poor, horrible, whatever you want to call it, you need to put a lot of information. So fellas, what they often do is, not so good, average, good. For you to get the very good and excellent, that means that's awesome. You want to get a lot of excellence. But let me tell you something. I've been declined. I received decline decisions after getting very goods and excellence. What that means? That means that the final call and decision is in the hands of that program officer. That's why you need to read that person. Okay, and you need to build a good relationship with that person. Okay, develop, like I said, a good long-term relationship with that program director, especially if it's a permanent program officer. Around 70% in the case of the National Science Foundation program officers are rotators. They tend to be faculty members that they take a leave of absence or so to go and serve for a few years in that agency. But there are another 20 to 30% that they are permanently there. You want to build good relationships with those. And very good advice that I give you is also offer yourself as a reviewer. If you want to get a grant under a specific call or program, there is nothing better than serve as a reviewer. Why? Because you're going to have in that panel access to an excellent proposal, at least 1 to 3 of them, that they're going to be funded, and the other 9 probably they will not. So usually 1/4 of the proposals that you will review, they will be funded. And you want to see what a winning proposal looks like versus a lost proposal, right? So that is a better kind of training that even participate in the webinars that they offer. What else? If the proposal is awarded, do not communicate with your officer just when is the annual review, the annual report due. Try to communicate every 6 months and even give them an informal update. Why? Because, you know, they like that. You know, that's how you build also a good relationship with the program officer. All right, let's look into proposal writing. So as I said, you need to look into, you know, and that two-page concept paper, the background, the goals, the expected outcomes. Also, a very important section is evaluation and assessment. Why? Because you need to demonstrate the success of your research. If you don't have a clear plan, then it might get declined, your proposal. Also, you need to identify what tools you're going to use to assess the impact of your idea. And last but not least is dissemination and outreach. Why? Because at the end of the day, let's say you're getting a federal grant, that is US taxpayers' money. So how those individuals not directly involved in your research and funding are going to benefit from it? You need to demonstrate that. So these are a set of questions that will help you to identify when you're doing that brainstorming process. These questions will help you to identify the goals, the objectives, the expected outcomes. I put them in here so you can use them when you practice. I'm not going to go over every question, but I want you to have this as a handout. So when you are doing the brainstorming, it can help you out, okay? All right, let's look into what is the typical criteria used to rank or rate a proposal. Under the National Science Foundation is based on 2 areas, intellectual merit and broader impact. Let me tell you something. Even though this government agency, the National Science Foundation, as also others, have tried to have, you know, or allocate an equal rank or weight to both areas, intellectual merit and broader impact. But let me tell you something. The reality is that intellectual merit has a greater weight or importance than broader impact. That's the ugly truth, okay? Now, what intellectual merit really means is how is your proposal contributing or advancing the body of knowledge in your field? In other words, what are you doing to innovate the body of knowledge? What is the scientific or engineering merit of your idea? Are you inventing something? Are you improving something? What are you doing? And then the broader impact is how others, as I said earlier, will benefit from your idea. Let's say you are doing a research that you think is gonna, I don't know, let's put an example, have some medical impact, then how others are gonna benefit from it. So maybe you might be using a population that are, or maybe it's a Department of Defense proposal and you're gonna be working with soldiers, fine. But then after that research, others will benefit. For example, GPS, right? GPS was funded and developed under Department of Defense, but look, nowadays, everybody pretty much takes advantage of that tool, right? So you want to identify that too in the proposal. All right, so what are the characteristics of an irresistible proposal? Well, it gotta be innovative and highly needed, okay? If you can demonstrate that nobody has addressed it before, or that that idea is a national or global priority, is fantastic. For example, my major professor used to say, Anna, the National Academy of Sciences publish very prestigious consensus studies that are highly regarded by many US government agencies. You probably want to start your proposal in the background, citing the recommendations of a National Academy's study and demonstrating that you are trying to tackle one of those challenges or implement a solution. So you try to look into that kind of literature review that helps you to demonstrate this is a national priority or a global priority. Then also, the idea must be clear, it must be feasible, it must be doable, and it must have a realistic plan. It should flow. The proposal, when you read it, it flows. You don't see gaps between sections. It just flows like, you know, in a very nicely way. It's perfectly written, no grammatical mistakes. If English is not your first language, like is my case, then you need an editor, okay, before you submit that proposal. What else? You need to write it having in mind that reviewers do not know anything about your program, your research, your idea. Why? Because sometimes I'm an engineer and I have been reviewing proposals for mathematics educators or for scientists. Do not assume all the reviewers in the panel have a degree and they are specialized in your field, okay? Show how others will benefit from the research. As I said earlier, the broader impact. Have a good evaluation assessment plan, a good budget, okay? It needs to be realistic, okay? When you read, you go over a budget and it looks unrealistic, it's another way that you lose, you know, credibility. Have the right person, a financial officer or an accountant helping you with that. What else? You need letters of recommendation and support from collaborators. If you're saying you're going to collaborate with this other expert from University X, that needs to be in there. It needs to be an evidence that that person is on board with you. And then finally, most agencies have proposal guidelines, okay? So comply to all of them. Often they give you a checklist. Just make sure you go over the checklist.
Hey,
all right.
Anna, sorry to interrupt. Just wanted to do a little time check here. I think you started about 10 after. We're about 20 minutes in, and so just to do a little time check, we want to give a lot of time for questions from the.
Yes. So, any questions so far? No. I think I'm gonna let the next speaker go, and then that way we'll have enough time at the end for maybe questions that attendees might have. What about that? Sounds good? Okay.
Sure.
Thank you.
Okay. So questions, I don't see any hands raised. If not, we'll move on to John. Thank you, Anna.
You're welcome.
And of course I was muted. Thank you, Anna. That was great high-level overview. And I think my intent here now is to get concrete and specific with examples. So I've highlighted the words from tenure track to endowed chair. So I'm going to try to provide for you a perspective from an early career researcher. And so the main goal that I have here is to show you how I started writing proposals and then winning proposals. And I'm gonna just be very forthcoming and show you real proposals and real numbers. And I'm not claiming they're perfect. I don't know if they would have all gotten excellence from an NSF panel, but some of them failed and some of them worked. So my hope is that I can point out to you what I perceive as, or what program managers have pointed to as weak points in failed proposals. And then I would like to contrast them with strong points in later funded proposals. So first of all, why are we trying to get funding? Funding enables our research. I'm seeing comments here. Are these for me? No. So funding enables us to do what we like to do, to research. Funding allows us to pay for personnel. It also allows us to purchase equipment and materials and supplies. And when you add all those together, you have productivity, right? Research outputs. We have papers, and ideally speaking, we're producing other PhDs and other researchers. So this is a snapshot of my group, and this is really what I would say is, my needs and what my desired outcomes are. And of course, I need to pay for this, right? So I have funding, which pays for my group. So I am the lead PI. I have 7 graduate students, 1 undergraduate, and 2 new students coming in the fall. And all of those students have to be paid. They also need a well-equipped lab in order to execute on our programs. And if we do all of that, if I have personnel and I have equipment in my lab and I have materials available, then we can have research productivity. And what, having a little bit of funding allows you to do these things. Having a little bit more funding allows you flexibility to be able to do these things, to be more creative, to be able to respond very quickly to an opportunity or a good idea. And so funding is incredibly important. It's an enabler for what we do. So very specifically, I currently fund my 7 graduate students on 2 NSF proposals. Both of those proposals, I'm a co-PI with 2 other PIs. And I have 1 student funded on an Army Research Office program where I'm the sole PI on that one. And I have 2 other students funded on an ONR program where I'm a sole PI on that program. One of my graduate students is funded through a fellowship. So these are just some examples. I have some NSF, some DoD, fellowship, right? You got to kind of spread it out. And then, of course, I'm hiring 2 new students in the fall. I don't know exactly how I'm going to pay for them yet, but you have to keep hiring because you only get an opportunity once a year to do that. And so if you didn't hire and then you do win the program, you're in trouble. So I'm going to keep hiring and I'm going to keep writing proposals. And if I'm lucky, they'll all just keep on flowing. The other thing that you need is equipment. So when you're starting out, you usually get a startup package. And my startup package, you negotiate that. And I was able to buy some really critical equipment for my lab. As I look back at my lab now, after I'm coming on almost 6 years in, that capital, that initial startup only covers about 20% of what I have in my lab now. All that rest had to come from external funding. And so, it's not just the personnel, it's the equipment that you're paying for too. And if you have that right, then you can be productive. And so that's why we're doing this. So I'm getting a little lag on my slides, I apologize. So here's a snapshot. This is from my research office. These are the raw numbers here. So in the last 5 years, looking at the right here, let me get a pointer. I have submitted 39 proposals. 20 of them have been funded. So that's a 51.3% success rate. I requested $21.6 million and was awarded $8.1 million. So this is not all to my group. This adds up co-PIs as well, right? If I'm a co-PI on a program. In the end, about $4 million went into my group. And so that is enough to pay for what I consider to be a healthy sized group, 7 graduate students, and to bring in materials and equipment so that I can execute quickly on new ideas and so I can execute on the programs that I've proposed. But that didn't all come right away. So what was going on in the first 2 years? So yes, I submitted 39 proposals, but in year 1 and year 2, I submitted 12 of them. You have more time in year 1 than you do in year 6 or year whatever to write a bunch of proposals. You're just getting started. You're not executing and delivering on 5 programs at once. So you should write as many proposals as you can in that first year. There's a lot of value to that, not just that you have the time. Of those 12 proposals, 3 were funded, 1 in the first year, 2 in the second year. And then it begins to snowball. But I really only brought in a little over 300K in that first year, and that was actually a DURP, so it was solely to equipment. And then 320K that I could actually start paying for students in that second year. And so, as I said, starting can be slow. So I encourage you to submit early and to submit often, especially in those early years. Write as many proposals as you can stomach, and you really just feel like you're a proposal writer. That's your job. You're just sitting there. You're brainstorming. You're writing. You're red teaming your ideas. You're submitting. You're getting rejected. You're getting rejected. You're getting rejected. You're getting rejected. Oh, hey! Suddenly you got funded, and then funding begets more funding, and that's the beautiful part. It's a virtuous cycle, right? And once you have funding, if you deliver, if you execute, and you report well on it, your sponsors are often going to say, hey, could you write for a follow-on program? We'd really like to continue funding you. So that's really your goal as far as you know, going to the follow-on programs. So when I write a proposal, I always remind myself that I'm telling a story. And Anna talked a lot about this. You have to be relevant, right? And so Anna suggested, you know, reading reports from the National Academy. That's an excellent idea. How can you show that your idea is relevant? It's not just something you are interested in, but actually intelligent people care about this. Or perhaps mission agencies care about this because they have a task to perform. So I encourage you to read the RFPs, the requests for proposals, and the broad agency announcements, the BAAs. Most of the government agencies, in particular in the DoD, they have these office-wide broad agency announcements. I'm showing a little screenshot here from the DARPA MTO, Micro Systems Technology Office. It's the office-wide BAA that was put out in March of 2020. In this is a list of like 30 things that they are specifically interested in. And if your ideas don't line up with that, perhaps you've identified the wrong sponsor. But these are useful ways of kind of letting your creative juices flow. Again, definitely look for grand challenges. If you can align your research with grand challenges, policy statements. In my area of research, I do a lot with electromagnetic spectrum. The DoD puts out an electromagnetic spectrum policy statement every couple of years, and I make sure to read that in detail so that I can speak that language. You have to be able to tell the story in the language of the reader. And if the language of the reader is, you know, DoD speak, then you need to be able to speak DoD. Attend industry days. Okay, so if you have an idea and it's relevant, you need to present your secret sauce, right? So I've got the McDonald's Big Mac over here. That's two all beef patties, such and such, and special sauce or something like that, right? That's why you go back to McDonald's, because they have that secret sauce. No one else has it. So what is it that you have? What's your novelty? What's your distinctive capability? Do you have a method? Do you have an analytical code? Do you have a theory? Do you have a fabrication capability that no one else has? Or is it some combination of all of those things? Think about really, really carefully, what is your secret sauce? Because a reviewer is going to say, well, yeah, I mean, anybody can do it. Anybody publishing in this area could do this. Why am I going to pay this person? Your proposal has to have a money figure. And I always ask myself the question, what's my money figure? And maybe there are multiple. But in my mind, the money figure is technical and pretty at the same time. Obviously, beauty's in the eye of the beholder. In my particular case, I think that propagating electromagnetic waves are beautiful. But it's technical in the sense that it proves that you're technically competent, that you can do a design or an analysis or something like that. In this case, I'm proving that I have in-house numerical codes and that we have designs that are doing what I'm claiming in the proposal. And it's kind of got maybe some wow factor, right? So some line is much bigger or higher than another line, right? So you got to have that money figure, whatever it is in your particular space. And then you need to be able to execute, right? Nobody is going to write a big check to somebody who seems like they're just totally scatterbrained and don't even know how they would execute on an idea. As Anna said, you can't have an Einstein idea, or rather you want an Einstein idea and a Shakespearean proposal writing, right? You need to have a concrete plan, and you need to have a team that can actually execute on that plan. And so, of course, you have to have a schedule, right? And it's got to have milestones. And it's got to have prototypes, maybe, if you're an experimentalist. So that's kind of the high level. I just want to make some really quick rapid fire general comments, and then I'm going to give you some examples of failed and succeeded proposals. So the high level is that you should always prepare, but sometimes submit even if you haven't prepared. And I especially mean that in the early parts of your career. Because you want to take as many opportunities to get funding as possible, but really at the beginning, you want as much feedback as you can possibly gather. Your ideas might not be mature enough initially for funding, but your sponsor, the program manager, in some situations is obligated to give you feedback, and you're going to get specific and concrete feedback as to why they didn't fund your proposal. So as I said, always prepare, but sometimes submit even if you haven't. The main difference between a good and a mediocre proposal, in my opinion, is time and effort. It's the same thing with papers, right? You can have a good result. The difference to elevate a paper to a truly fabulous paper, or a proposal to something that's irresistible, in Anna's words, is really putting in the time and the effort. You've got to make that story flow. You've got to make those figures beautiful. They have to pop. They have to show exactly what you're trying to show and not more. Can't be distracting. But as I said, sometimes it is worth just submitting. You might get lucky. The idea might be so good that even a poorly described version of it is worth funding. And you don't want to miss a submission deadline, right? Because sometimes they only come around once a year, or maybe that program is gone now. It's also a good excuse to generate ideas. It gives you a deadline. Sometimes creativity is difficult, but if we have a deadline, it's really surprising how rapidly you can develop an idea. And also the preliminary results that you put in a proposal, if you do it right, they could possibly even be used in a publication later. So it's not a wasted effort. So I would encourage you to take many swings at that. I'm not going to say most of this. Just a couple of key things. You need to be active and you need to be visible. You got to have a website, and you should be at conferences talking to people. I've actually gotten funding, cold calls that resulted in funding just by having a website. And by writing what I thought were, just little conference papers, just reporting on what we did. Well, somebody read those and it was, it ended up working. Visit program managers. This, when you first start out, is quite intimidating. You might not think that you've got an idea that's big enough or grand enough or complete enough to visit a program manager. Nevertheless, I encourage you to take a trip to DC and visit as many program managers as you can, come with a white paper in hand, and pitch your ideas. You'll get feedback. Best case scenario, they say, yes, I like this idea, please submit a full proposal. Worst case scenario, you got some really good feedback and you got extremely honest criticism of an idea so that you don't have to waste your time. Also, look who funded papers in your area. If you have an idea that's related to some of the literature, look in their acknowledgements affiliations section down there, in the lower left corner of the IEEE papers, and they'll show you the program award number, or maybe in the acknowledgements section. And that's a great way to find out who funded this work. And you might be surprised to find out that, oh, the Army's interested in that? Oh, okay, great. There's a whole new avenue that I didn't know about to get funding. And then I'm just going to highlight this last bullet here: deliver. The easiest proposal win you will ever get is an invited follow-on to an existing program in which you've delivered. Those are the best kind, right? It takes you almost no time to write the proposal, and it's nearly a slam dunk. So you really want to go for that. You got to keep the ideas flowing. And one way to do that is to keep up with the literature. So I have a bunch of these Google Scholar searches that I get emailed once a week with keywords. So you can go onto your Google Scholar account, create one if you don't have one, and I'm just going to say alert query millimeter wave. Create alert, show up to 10 results, and it'll email me once a week on results in that area. I find more papers that I was not going to be aware of because I wasn't doing a good job of reading my journals every month. But my Google alert, notified me. Also, as I said, writing proposals is a great way to focus your brainstorming. And then query your existing sponsors and your contacts, because a lot of times the good ideas come from applications pulling on your technology. So it's often a combination of pulling and pushing. And then when you're writing, I like to think about what are my adjectives and what are my verbs. No one wants to fund an engineering effort, right? You've ever heard somebody say like, oh, well, the rest is just an engineering task. Well, I'm an engineer, so I don't necessarily see that as derogatory, but research that's worth funding is not just an engineering effort. It's got to push the envelope, advance the field. You know, I'm not just making an antenna. I'm not just making a such and such. I'm making a compact antenna, a conformal antenna, a wideband antenna. What are your adjectives? And that's, you gotta just keep those, you know, focusing your proposal, because you want the reviewer to leave after having read your proposal with some kind of summary statement in mind, like, oh, they're using an, you know, insert your favorite adjective, lens to address a particular acute pain point, and they're going to achieve X dB or X% bandwidth or something like that. So if they're going to say, oh yeah, I just reviewed this proposal, it was good, they're going to, you know, one sentence, what is it? What are the adjectives? What are the pain points? And what are the numbers? So now I just want to show you 3 proposal examples. The first one is an NSF proposal. It was funded. It's to the NSF SpecEase program. I'll tell you a little bit about that in a second. It was very cross-disciplinary, and it was sort of, I would say, very scientifically structured. We structured the proposal based on fundamental research questions, and then it sort of unrolled from there. And then the other 2 proposals are one to DARPA and one to ONR. They're both very similar proposals. One of them was not funded, one was funded. So I'm going to do a side-by-side comparison there. This is more kind of technology prototype led, not fundamental research scientific question led. Both are completely legitimate sorts of proposals. Often it depends on the sponsor. So the NSF proposal first. Again, this one was funded. It was to the Spectrum Efficiency, Energy Efficiency, and Security program at the NSF. And basically, and they were specifically requesting cross-disciplinary teams in order to address these issues of spectrum efficiency and energy efficiency. And so myself and 2 colleagues here at the University of Notre Dame, I was at sort of the hardware level, and my 2 colleagues are at the comm theory, information theory level. So we sort of spanned this large stack, if you will. What we were basically doing is related to millimeter wave massive MIMO, which is where you combine very large arrays of antennas. And we were saying, you know, given these very wide bandwidths, very high frequencies, and a large number of elements, the power and the cost are prohibitive. So how can we fundamentally remove those barriers? And so we're going to completely reimagine the radio, right? We're going to throw out conventional design, and we're going to go with the simplest possible radio, which is like throwing a nonlinearity into the world, and you see what you can do. And it turns out you can't do very much. But if you combine it with some really clever analysis and theory in a large system, then you can recover all that performance. So that was our sort of key insight, was by combining these things, you can reimagine a traditional thing. And so the way we structured the proposal was around these fundamental and what we thought compelling questions. So we formulated 3 research questions which guided and motivated the rest of the tasks. And then we came up with specific tasks related to those research questions. And then for every one of those, we showed a preliminary result. So here is, I just pulled some screenshots from that proposal. This is our executive summary introduction. The proposal was titled Wideband Wireless Communications with Low Power Transceiver Cell Circuits. We probably could have done a better job with the title, but right away we got into the proposed research. It aligns along its tasks along the following questions, and there are 3 fundamental research questions. Number 1 is, what are the performance power trade-offs in building efficient 1-bit transceiver cells? And then the other 2 questions were sort of, what are the theoretical limits for capacity, and what algorithms can achieve these limits? And then basically the rest of the proposal was addressing those questions. So if we've done a good job of formulating compelling questions, then we have our outline. So I'm not going to read through this except just to show you the outline. Our research questions were, what are the performance power trade-offs in building efficient 1-bit cells? So now the next section, 2.1. performance power trade-offs in the design of transceiver cells. It's nearly word for word. You don't want to hide your outline. You don't want to make it hard to read. You want your reviewer to know, okay, they're talking about question number 1. And then very quickly, we have a preliminary result. We have designed something and we've simulated it and we've analyzed it. As much as possible, you want to throw in things like, oh, a shocking observation. And then, you know, something aggressive and active, right? Rather than the conventional solution, we propose to strip away, you know, something very active and aggressive, right? So the language is kind of high energy. So now we have the 3 questions that motivate the sections, and we're going to put preliminary results. And then you need details here along with the money figure, and then you have your tasks. So again, I'm not going to read this except to show the outline. So here we're in this kind of question 1 details section. We went through the preliminary results. We now have some detailed discussion, presumably with some money figures in there, and then the proposed task. And we're going to just very specifically list out what the task is. And part of this was later used to justify the budget. We needed to justify the expense of the experiments and the prototypes. So in this particular case, we had to argue that large systems were modeled with overly simplistic analytical models, which leads to erroneous conclusions. Therefore, we proposed to actually develop these things and generate fresh models that could kind of allow us to advance the science and answer the fundamental questions. So that's the NSF, more kind of scientific inquiry, 3 research questions motivating the rest of the proposal sort of outline. Now I'm going to put side by side these 2 funded and not funded proposals. So the first program that I pitched to was the DARPA ISCL program. That's the Inter-Satellite Communication Link program. And that was not funded. The goal there was to provide the highest data rate between microsatellites consistent with their small size and limited power. So this is a size, weight, and power swap constrained platform, small satellites. And you want to get a lot of data from satellite to satellite over very long distances and over wide fields of view. You need to be able to scan antenna beams. So, you know, phased arrays are a possible solution, but of course they require a lot of power. And so we were pitching a lens antenna based approach, which could have very high gain and be very low power. And then the other proposal that was funded was an Office of Naval Research ONR BAA. Now, this came along from white papers, networking, and then being asked to submit a white paper, which then got asked for a full submission. And they just told us, go look at our office-wide BAA and write to that program. So this wasn't me looking for a program to pop up and writing a proposal. It was years of, and I'll kind of outline the years of activities that led to being invited to write the proposal. And the goal was very similar: provide a wide field of view beam scanning antenna for high power applications. That's not high power consumption, but high power like radar, with extremely high radiation and aperture efficiency over wide bandwidth. So very similar technical challenges to the first program. So like I said, the program goals were wide field of view without loss as you go toward the horizon, high efficiency, high quality beams, low side lobes, and very compact. So the successful proposal should address these goals by identifying the challenges, proposing novel solutions, which we then show to be effective and within our reach. And so here's kind of the high level kind of proposal figures. On the left, we have the not funded proposal, and on the right, we have the funded proposal. In the DARPA unfunded program, we pitched 3 technology components in a system. The first was a GRIN lens. The second was a matrix of vanadium dioxide switches, which are very low loss, and we thought could be used to route transceiver signals to and from a feed element array below a lens. And then the third was high efficiency millimeter wave amplifiers. So I'll get into some of the weaknesses there in a little bit. The ONR program that was funded is very similar. We have a lens antenna We have one feed shown here in color. The others are kind of grayed out a little bit, but we have a feed array below the lens. But in this case, we have a few more elements. We have an optimized curved surface aperture lens. We have a feed element with another corrective lens, we called it, on top of it that does some very specific things. So what was the weak point of the program or the figure on the left? We didn't identify any challenges. However subtle, we just said, here's a block diagram. This is what we're going to build. It doesn't really jump out at you. The problem doesn't jump out at you. Now, I'm not claiming this is the best figure in the world, but what we tried to include in this figure was some notion of the challenges. So I've sketched this little red arc here, and I labeled it the Petzval surface. And in the narrative, we described that that's the optimal surface in which to feed this lens. But we would like to have our feeds on a flat surface for cost and fabrication and a bunch of other reasons. And it turns out that's hard. And so right away, you see in the graphic, oh, that's going to be hard. And so we've identified graphically a challenge right there just by putting in that red line. The other thing we identified was, here's this feed. Normally, the radiation pattern from this feed is just going to go straight up, and we're going to get all sorts of spillover radiation. It's not going to intercept the lens, and it's not going to do what we want. And so here again, you have a little detailed graphic showing one of the challenges, spillover. And so right there, you've got the challenges identified in the key graphic of the program. Another thing is that we have cartoonized results instead of notional sketches. So now we've matured our design and our analysis and our simulations and our methods to the point where we actually could design some of these things and get some notional patterns out. Here you just see a sketch, right? This is like literally PowerPoint engineering over here. This is a 3D model in HFSS, or pick your 3D modeling EM simulation software. And this is a real permittivity profile. And we're not sure at this point if it works well, but there's actually real permittivity values described there. So this is actually a design. It's not notional, right? And that gives us credence. We're also leveraging past successes. So we're citing some of our publications and some previous programs where we've shown that we're good at designing these things, but then we add a new twist. So now we're going to optimize these curved surfaces and not just make the flat lenses, because we're now trying to push the envelope in scanning to the horizon. And so we need everything that we can to throw at that problem. And yes, this is graphically dense. So if you're a graphics artist, you might not like my graphic, but it is information dense. It shows you a lot of information. And so the two research elements there were this optimized curved aperture lens and these corrective lenses on the feeds, as opposed to sort of three very disparate technologies in this program here. And that's, I'm going to come back to this slide. Really, that was kind of one of the main weaknesses of this proposal. So weakness number one, and this was identified by the program manager, our grid media lacks novelty. You could have just found this in the literature several years before we submitted this proposal. So why does the program manager think we have any hope of accomplishing their mission objective, which is to push the envelope of what's possible? We're not offering any new insights or any new fabrication capabilities or anything like that. So we didn't have our adjective. We just had grin, but that was already done a long time ago, right? When it came to the funded proposal to ONR, we had now matured our technology, and we had a bunch of different adjectives. It wasn't just grin, it was intrinsically matched grin, so we could be wide bandwidth, and we have nice graphics to show that. It was an optimized curved aperture lens so that we could get beam scanning. It was a feed corrective lens to compensate for aberrations, right? So we had a lot of adjectives, a lot of detail to show. So how can you then overcome the state of the art? And here you need to show theoretical limits and what we can accomplish, right? And in our proposal, we showed, look, you start here, you add our technology, and boom, you get improvement, right? So you got to have something like that where we're approaching a theoretical limit or the state of the art or something. What else was bad about that DARPA proposal? The VO2 switches seems novel, but we failed to show why this was the perfect solution for the switch beam feed problem. And we also failed to show why people doing the lens antenna could also do device development of vanadium dioxide. We did not have collaborators that were material scientists, so we couldn't innovate here. It was just like we hoped we could find, you know, some way of integrating those. So it was not believable. We didn't have a team in place. Also, these millimeter wave PAs, they just seemed like a complete add-on. Let somebody else do that in another research program, right? That's not critical to the success of this task here. So we omitted those. They're extraneous, right? You got to focus our proposal down. Now, in my defense, this was one of the first year proposals that I wrote, and I was just sort of got a million ideas, and I was interested in all sorts of things, and I was just trying to get them funded, right? But I overreached, and so I had to focus. And then in the O&R proposal, I also showed deliverables, very concrete specs, prototype 1, prototype 2, prototype 3. I worked with the sponsor to define these metrics. And so now let me go back really quickly to show you the interlude between these two proposals. So I wrote this proposal to DARPA very early on in my career. It was rejected. I scheduled a meeting with the program officer requesting feedback. Eventually, we finally got that scheduled. The program officer gave me some very concrete feedback, which I've already discussed. You know, lack of novelty, seemed very, you know, kind of thrown together, don't have a viable team to do a tech transfer, and so on. But I believed in the idea, so I continued pursuing the research. How? Seedlings, little tiny bits of money. First, I had only discretionary money and undergraduates. That's not a lot of money at all, and somebody I didn't have to pay. But we were able to get the ball rolling. And then eventually I got an USNC-URSI seed funding of 40K. That's not a lot of money, but it was enough to pay for a grad student for 1 year. And then I finally got preliminary data. We put in 2 conference papers that year. And then I got contacted out of the blue from somebody in industry. They found us on our website and they read those conference papers. And we had a really good conversation. They said, hey, it sounds like you have a lot of good ideas. We'd like to fund you. And it was a small amount of money at first, but it got us started. It got us in the game. Industry funding is great because they provided a ton of input. They really cared about the success of this program. Because if it succeeded, then they would succeed, right? They were invested. The downside is it was very applied. It was very hard for us to figure out how to publish on that money. Not that we were disallowed, but rather we were so busy delivering that you couldn't just sit back and think about the fundamental questions. So that's the downside. But often the initial money is that way. But then you want to structure your final funding to have room for some of that more fundamental stuff. So how did I finally get funding? Based on this industry work, I'd been, shopping it around to colleagues and various other people, whoever would listen. And one of my colleagues said, hey, I have an O&R sponsor who's coming for an on-site meeting. Would you like to give them a 10-minute briefing of what you're doing? It's sort of related. So I jumped on that and put my best foot forward. Then they asked us to submit a white paper, and then finally the full proposal. So the key here is that a good idea might be rejected initially. Why? A ton of reasons. You could have been immature in your technology, right? You just needed a little bit more time. Doesn't mean there wasn't something gold there. You just didn't have it yet. So keep on pushing. Be sure to follow up and stay engaged. That's the key takeaway from this story here.
John, just to quickly interrupt, we're just a little over 1 hour through our 2 hours. I think you've been, you started about 30 minutes ago, so. Just
okay. So I think that's actually the end of it, basically. So at this point, I guess I can ask, Jeff, should I ask for questions now or save them for later?
Whatever you like. Yeah.
Well, let's see if there are any questions at this point.
I have a question. I want you to tell me when you're proposing in some program so I know to pay attention, because you're in competition.
probably I'll keep my cards close to my
I think we can now write the joint one. You're not a student anymore.
Yes, yes. Yeah, that's the other thing. Be careful about writing proposals with your former advisor until you've established yourself.
Yeah.
Well, if there aren't any questions at this point, I think now is a good opportunity to segue to our next speaker. So what I've hoped to do here is give you an idea of what it's like to start out and some of the mistakes that I made early on, and hopefully learn from them. You know, at this point have good funding to maintain my research program. But of course, there's a long game here, right? I'm just on the tenure track. With, you know, assuming things go well, I'd like to be in this game for many, many more years. And so our next speaker, Zoya Popovic, is very successful and has run a sustained high-level research program for over 30 years. And she's going to tell us how you can sustain upwards of $1 to $1.5 million per year in funding to keep that robust per year to keep that robust research program alive. So I'll pass it off to Zoya next.
Yes, but just quickly, we do have a question, do have a hand up. Go ahead, Arash, introduce yourself and ask your question.
Hi, this is Arash. I'm a PhD student at the University of Arizona. Thank you so much for your talk. It was amazing. I learned a lot. And my question is, the tips and hints that you gave us, do these only apply to like professors? Like I'm a PhD student, so what can I do as a PhD student to get ready for like proposals?
Yeah, okay, so great question. First of all, so actually just like Anna, I told my advisor that I was interested in writing a proposal with her. And so Zoya.
So he did, and he got it funded.
Yeah, we got that funded. So I had seen, before I left grad school, I had seen a successfully funded NSF proposal. And, you know, I went back and forth with Zoya many times, and I got to see how she, you know, I talked about telling your story. Well, she's good at telling the story. And it was hard for me to figure out what the story was. Why? Because as a grad student, you're in the details. But you know, nobody cares about the details until they care about the big story, right? And so my encouragement to somebody who's currently a graduate student would be to look at your technology, whatever you're working on, but look at your competitors too. It's, you know, let's just take as an example, I was showing some lens intent applications. A direct, you know, a competing technology would be a phased array. I am not by any means saying that there isn't fabulous and important and revolutionary work being done in phased arrays. So I have to be very aware of what's going on in phased arrays. If I want to tell a good story, I need to be aware of all those things. So as a graduate student, and this is of course helpful in writing papers and for, you know, defending as well, you need to have that big picture context. And so I would very much encourage you to set up those Google Scholar alerts to keep you up on reading the literature. You've got to keep up on the literature. And then also, read BAAs. They are extremely overwhelming. It's just 45 pages of dense content, but somewhere in the middle, there's usually a couple of pages of really nice technical narrative where the DARPA program manager and their CETAs have, you know, gotten together with a bunch of other, you know, successful researchers who've submitted a bunch of white papers and ideas that eventually get, you know, folded into these program announcements. There's a lot of good work that's already been done in there. Motivation for why somebody wants to do a particular project, what the fundamental limits are, what's the state of the art, and what they're looking for. And so I would encourage you to go read, in particular, I like the mission-based agencies, DARPA, you know, any of the ONR, ARO, NASA, DOE, IARPA, these kind of agencies, they have a mission. And therefore they have a problem space, and it really helps to focus the technology efforts. So yeah, that would be some of the encouragement I would give you as a current student.
Thank you.
So John, we've got another question in the chat. So the person that asked the question in the chat, maybe you'd like to ask your question.
Okay, so I see, is this the question,
Yeah.
Yeah, the last one there. Okay, so Dr. Chisum, any situation where you thought it was scientific advance, but reviewers felt it's just a technical advancement or an engineering effort, how did you deal with it? So I'll say this, nothing immediately pops into my head, but what does pop into my head is that when the reviewers said it wasn't scientifically advanced, or, you know, insert your criticism there, upon further reflection, honest reflection, I realized that my idea wasn't complete yet, or it wasn't mature enough, it wasn't articulated clearly enough. And so usually people are good at identifying good ideas, right? So I would say that if the criticisms come back that it's not, you know, of scientific merit, or not, you know, novel or fundamental enough or important enough, and it's just an engineering task, let's say, you know, I might balk at that and say, oh, I disagree. But then if I go and look at my proposal, I realize, but I didn't actually, you know, because somewhere in my heart, I know that there's something really important here, or I feel it, you know, and, you know, that's, everybody has their own, you know, kind of opinions there. But if you didn't communicate that, then that was bad on you. So you got to go back and figure out, well, maybe I didn't talk about a fundamental limit. You might be right that your engineering idea is a really good one, but if you didn't show them that it's, you know, a key way, maybe the only way, or a viable way, or a compelling way to sidestep a limit that's being hit in the state of the art, then that's what you have to go back and do.
Thank you, very helpful.
Yeah, I would add that it's really important to do a careful literature survey here and show how your idea is improving upon what has been done. It's completely critical.
Okay, very good. Thank you, John. Thank you for those who asked questions. Let's go ahead and move on to Zoya's presentation. And, you know, time permitting, there'll also be opportunities to ask all the panel members questions at the end.
Okay, thank you, Jeff. John did an outstanding job, and so I will just be repeating a few things that Anna and John said, but maybe in a different light and maybe with a little bit more experience. I'll also try to give you some concrete examples. You know, when you become older, like I am, you have an awful lot of things to do. And so there's very little time to actually worry about writing proposals, and even less time, unfortunately, to do real research. So you have to be really careful with time management. On the other hand, you do have the benefit of having more experience and you're a little wiser, of course, until you start getting senile. But so it is a different ballgame, and I don't, both have benefits, being younger and being older, I guess. So one wonders, how many proposals should you write? John told you about his statistics. I wish I had mine. I don't have it. But I've raised on the order of 45, 50 million over the past years. And the key thing is that so I can talk as a professor, but it's not that different for my students who are in industry. You have a lot of stuff to do. You have to multiplex, you have to teach in our case, you have to do the research, you have to get the funding, you have to find good grad students, you have to advise, you have to write papers, you have to review papers, you have to be fiscally responsible, you have to watch for things to do to help the department, you have to do project reviews and reports, you have to make sure old ideas work and come up with new ideas and serve on committees you believe in, and somewhere you may have to juggle a family. And so it's really critical to do your homework in advance when you're writing proposals so that you maximize the chance of getting it, because it's just a lot of time that you have to put into this. So I'm going to try to tell you some strategies maybe of how to increase the probability of getting your work funded. Having said this, I want to say, I really want to echo what John said. The really main reason why you want to do all this is so that you can do your research, and it should never be set aside. You never should forget that. It's easy to forget it because it is a game and we're all competitive and we want to, show that we know how to do something, but ultimately you should focus on the research. At least that's my experience. So there are very different modes of funding, and Anna touched on this as well. She gave a different list than mine. I put all these things in different colors because these are very different agencies to get money from. And you can see that by looking at their signs. They're all different also. And they have different styles. And so that means that the program managers that you work with are going to have a very different perspective on things. And it's really worth figuring this out. So in the DoD, actually, the agencies are also different. DARPA funds very high risk stuff, but they have a lot of money, whereas the Army Research Lab, and so on, they don't have as much funding, but they will fund, I would say, more less risky, work. The NASA, I find, is quite different actually than the Department of Defense. And there you have to kind of be plugged into the network a little more from my experience. NASA also depends a lot on congressional funding, a little bit more. And so I've had cases where, a giant program was pulled under our feet for no reason except that politicians decided not to fund it, like a mission to Mars, or something like that. So industry is very different. John alluded to that. I'll give you a couple of examples, but it's really worth working with industry, especially if you're an engineer. And then Department of Commerce, such as NIST and Department of Education, are also other sources of funding, again, with their own idiosyncrasies. NIH, I haven't been able to figure out, but they have a huge amount of funding, but it looks like you have to work with a doctor to be successful there. Then there's centers and collaborations. These are important ways, especially for not just for younger faculty or younger people, but also actually it's really good for more senior ones, because in the end you get old and maybe people don't want to fund you. They figure you already have your funding, but then you should work with younger colleagues and freshen up a little bit. And then finally, I've had over the years a lot of fellowships. My students have a number of fellowships. You can feel free to ask me questions about those. And then gift funds from, from private people all the way to companies that decide that they would rather give you a gift. And I mean, by a gift, I mean a sizable gift, 100,000, a year, just because they want to have access to your research. So these are, in my view, all completely different ballgames. So I have a lot of experience with the Department of Defense because of the field that we're in. And so I wanted to give you some tips for DoD proposals and maybe a few anecdotes. So they're the military labs. So these are Army Research Lab and Army Research Office. It's kind of one thing, and then NRL and ONR, and finally the Air Force. Here, the distinction is that the program managers can be for decades in the same position. And so it's worthwhile cultivating a relationship with a program manager over the years. And they're also interested in people making progress in the longer term. In general, the Department of Defense understands the long-term nature of academic research and of research in general. John already told you, learn the needs of the program, read the BAAs, try to understand every word that they're saying. And then the other thing that's critical, I think, is to propose the right amount of work and funding. I know colleagues who propose ambitious work, or maybe even not so ambitious work, but would like a lot of funding because there's pressure from their administration maybe. And that's not the right thing to do unless you're really set up for it and have shown, really success in a previous project. So it's good to start small and then prove yourself. And then it's on bigger projects, you want to work with industry on joint proposals, because everybody knows that someone in academia cannot really, accomplish the technology part. If you're not going to be an academic, and if you're on the industry side or the national lab side, then I would say work with an academic, because they give another perspective to things, but not only that, because they train your next employee. DARPA is different, high risk. Also, they tend to prefer when a university works as a subcontractor to a larger company, and that means that it's more complicated actually to write a proposal. Having said that, I'll show you an example where this is not true. This was not true. And the distinction is that program managers stay at DARPA a limited amount of time. And in fact, they'll put a program in place and then they leave and the program gets inherited by another program manager. And so it's a lot more work to cultivate relationships. However, what I've found is that so-called SETAs, and these are helpers of DARPA, you know, they're actually another company like Booz Allen, they have a bunch of names. And these are people that do research for the DARPA program managers. And some of these stay forever, you know, decades. And so it's worth getting to know them. And they're also quite competent and they love their jobs. And the program managers listen to them. So it's worth talking to the SETAs as well at DARPA. And for DARPA proposals, I would say it's helpful to know how to draw beams going all over the place, even though nobody can see these beams, and this is not what these beams look like, actually. I'm joking a little bit, but on the other hand, what this really tells you is that you should pay attention to what John told you, which is to read what they want. And this is from an old DARPA webpage. Now you can see interconnected chips on the DARPA webpage. Very different ball game than maybe 10 years ago. Getting funding often takes a lot of preparation, but it's worth it. It's an investment. So everybody told you, talk to the program managers. The thing I want to tell you is that you want to help them make a program. They need help actually, and they want help. They advertise that they want help. And so they want to hear your ideas. And a good way to do that is to get something called a seedling. And that means that you talk to the program manager and you tell them, look, I have a good idea. You know, it's in your general area of interest. I've done my homework. I know what you do. I speak your language. Your background is in so-and-so. My background is a little different, but I can help you out. And they can give you pretty painlessly a couple $100,000 over a couple years to help them get a program started. This is an excellent, actually, mechanism also to learn about what they really want to do and to get ideas for good research, you know. In that process, you can also find a company or many companies that are good for teaming, you know, people that have labs and fabrication and things that you don't have, but who may need your expertise. And there it's important to identify what your unique part is, because everybody knows you can't do everything. And so it's very important to carve out your part so that people can depend on you. But then of course you have to deliver because everybody depends on you. Usually a DARPA program will have several technical areas or TAs, and only some of them are actually intended for basic research. So you have to do a very careful job at reading the BAA, which John already told you, and finding out which of those technical areas is really open to you. Actually, some of these will be classified or ITAR, and so you, as a university, it's very hard for us to work on those. So here's a successful DARPA proposal and how it became. It's called the micropower conversion, and I'm told it's not on the DARPA webpage because they view it as an important program. I felt it was very successful, so I asked them, why isn't it on your webpage? They said, well, we don't put all our programs on the webpage. I didn't know this. The initial program manager was John Albright, and after that it was inherited by Dan Green. John basically was there less than a year because it takes them a few years to set the program in place and then they have to go. So I met with John in Washington, learned about, before that, read up about what his expertise was. We discussed his interests, and he was not intimidating. You know, some of them are, most of them are really nice people. It turned out we had a mutual interest. And so I followed up immediately with some ideas, and it turned out that some of these ended up in the announcement itself. So I helped him make the program. And then I identified colleagues in my department and the company with the right technology so that we were set up and waiting for the announcement to come out so we could react very quickly. these are some of the things that I told John that ended up in the BAA. So when the BAA came out, there was a technical area 1, which had device technology development, which was not definitely appropriate for a university. And it turned out we were able to work as a subcontractor to Corvo in this case. So they built chips that we designed, which you can see here. And then there was the technical area 2, which was more circuit development and kind of co-design. And we were there a prime contractor, which is very surprising for DARPA, that a university is a prime, and a company was our sub. So out of $5 million, Corvo got $4.5 million maybe, but they were our subcontractor. So in this case, the white paper was 15 pages long, so it was quite a bit big. It was basically the size of an entire NSF proposal. And the full proposal was about 50 pages long, so quite a bit of work. And surprisingly, this ended up being a grant because this saves the government money because our overhead was lower and it was easier for them to administer because we were the lead. So my point is there are all kinds of mechanisms that this can work with. And then I want to show you here, you see a circuit here that we ended up making, but the point is that the proposal had a curve. This maybe answers one of the previous questions. And this is what the state of the art is. And we actually drew the curve over what's a little bit over. So that's the fundamental limit. And then our new approach are the little green dots above this curve that show, we have a new approach. Pay attention because it's going to get us higher above. And we actually had some experimental data to prove it. So to show you how I helped the program manager make the program, I asked, can I actually compete and be a prime? And he wrote me an email. I hope he doesn't mind I'm sharing this. This is a long time ago. He said, I would be happy to see a TA2 proposal led by university. Great, my question is answered, I can do it. And then at the end, he said, it's not surprising that people are asking you to team up. And I didn't even reference you in the BAA. So clearly it was great. It was great that I was able to be helpful. An example, in our proposal that's a little bit different is for the electronic warfare program. This one is actually ongoing, this project. It was intended for companies in this case, but it did have a significant research component that you could find out by reading the BAA. And so we assembled a strong university team of 4 faculty and 2 of the co-PIs, myself and Taylor. We already had ONR projects in the past, so we had a good track record. And then we included 2 other junior faculty that had complementary expertise. And we targeted a reasonable budget that we know would be very competitive with any company. We're basically cheap. And we had concrete milestones similar to the table that John showed you before. So the proposal components, which were unique to our team, is that we had documented great industrial collaboration. These are companies who wrote us letters who said that they want to hire our students and they'll help us with fab. And then we argued that we're really training a US workforce because that's what the government needs. And then we had a system level plan so they understood how they fits into their kind of overall mission. But we pointed out component level research where the innovations were happening because that's more appropriate for the size of team that we are to do. And so it's important to have a strong page 1 that really illustrates what you're doing. I'm not particularly proud of this figure. I ran out of time, so it's not as good as John's figures, but it does tell the story. And the story here was that we're developing a unit element that fits into a very scalable system. And actually we're not proposing even the whole system, but just one of these subarray things. And then we came up with a title that a lot of people called us, and reviewers called us and asked us, what does this mean? Can you explain this? And actually we did explain it, but they didn't read the proposal properly. And the title is, GaN, so that's a buzzword. And that's what we're doing, gallium nitride transmitters, okay, with 5-dimensional reconfigurability. And so in this case, we were reconfiguring signals, power, beams, all kinds of things. So it's important to have a very descriptive figure right in the first page that describes what the approach is and some of the key things about it. This is an example of a proposal that was funded with very little effort. So we had a small part of the DARPA DAHI program, HRL included us in this because they wanted to use our chips actually from a previous program. So that's leveraging off a previous program. We published a paper, it got noticed. And then the Air Force found it and they just said, send us a little description. We'd really like you to continue this work. So there was no competition in this case. We just submitted a proposal. So my point is that a lot of stuff, if you get good results, you can leverage it by appropriately telling people about what you did. It's important to report for the DoD, send reports on time, participate in all the telecons. If the program managers are too busy and are not scheduling them, you may have to ask them. I've been in this situation many times because they do want to find out, but somehow they put you on the back burner all the time. But if you bug them, it's a good thing. You want to stick to the time because make it even shorter. They will, if you go to one of these meetings, you know, and they give you an allocated time. I've been in situations where they put this big red clock in front of you and it's ticking down seconds and you have to make it in exactly the right amount of time. It's pretty intimidating, but therefore prepare a shorter presentation. How am I doing on time, Jeff? Because I don't have a clock on my screen.
It's 36 minutes after the hour, so we have roughly 20 minutes total, 20.
I think I started about 20 minutes ago, or maybe 25. I don't
right.
have to, I think I just wanted to maybe give a few little hints and then people are welcome to ask about any of the other topics.
Great.
I just want to say a few things about NSF proposals because that maybe, although Anna really addressed these very well and so did John, there are three different really kinds that I've been involved in. One are individual PI, small proposals. These are great. For these, it's useful to be on panels so you see how you'll be evaluated. Keep in mind that each panel is different. You could submit once, get rejected, then the next panel, same proposal, accepts it, you know? So it's a little bit of luck. Then there are these large center type proposals. They're a lot of work, a little bit of a pain, and low payoff. There's a fixed amount of money divided by a lot of people, but they're very important for visibility. So you may want to do that just so you can advertise your work. And then there's the commercialization ones that are SBIRs, STTRs, and there's something called the PFI program and the I-Corps program. And I'll give you an example of something that might fit some people's interests here. The important thing for NSF is education and outreach. A lot less important for a lot of other agencies, although it should be. Diversity, equity, and inclusion, a big part of it. And finally, the transformative nature of research. You have to show how what you're doing will really change something. You have to show this in DARPA as well, but they don't use the same language. So I want to show you an example of one of these commercialization ones. So we had a NSF funded proposal in core body temperature measurement using microwave radiometry, which is dear to Jeff's heart, maybe. You can use it in the near field, Jeff. You don't have to look at stars. And out of that came a patent, which is only because some of my students wanted to learn how to write a patent. So I told them you can go do it, and they submitted a disclosure. So NSF will fund commercialization, especially if you've had an NSF funded project that resulted in a patent. And this is pretty interesting. So right now, you know, they also train you and they teach you how to make a company. So there's someone in our area who decided they're going to license this patent and make a company out of it, and they're going to fund my group. So that's just another interesting thing about NSF that may have not been mentioned before, so I thought I'd mention it. I want to show you a failed example of a proposal and tell you how it happens. This just happened this year, or 2020. So this was a proposal with environmental engineering colleagues, myself in electrical, and the National Renewable Energy Lab down the road, to the Department of Energy. You know, so they are, NREL is the Department of Energy. So you'd think, okay, that's good, a good team, a shoo-in. It had 3 phases. First, a white paper, 4 pages, It passed the initial review, invited for a full proposal. Then the full proposal was 40 pages, factor of 10 dB right there. And it was evaluated positively. And we received 2 consecutive rounds of follow-up detailed questions, including like, could you reduce the budget a little, blah, blah, which to me, if you were working with another agency would mean a shoo-in, right? And then they said it's rejected. And the only feedback we got, even though we requested feedback, was, well, this topic wasn't of interest. Really? And it took you a white paper and 40 pages and all these questions to tell me this? My point is, sometimes you have no idea why something was rejected, but you may think it's a good idea. In this case, I think this is a very good idea. This is about how to use microwave high power to convert waste into usable fuel. And this was particularly for biowaste, pyrolysis it's called. And I really like these colleagues that I worked with who are chemists who know this stuff, and we think it's a great idea. So don't give up, don't give up if it's a good idea. Just now I found through an ARPA contact, he put me in touch with a bunch of people. I got 4 emails that are really interested in this, and I have a call with them tomorrow morning. So, if it's a good idea, you have to keep pushing it because sometimes you just don't know why it was rejected. And so working with industry, John already told you it's shorter term, it's very demanding. But what they need are well-trained people. They treat you like cheap consulting, so you have to be a little careful there. And this is for commercial. This doesn't hold for the Lockheed Martins and Raytheons. For them, with them, you team up on DoD. But there's some really good opportunities working with industry, and that is you add on to existing work with which, just like John's lens antennas, you establish collaborators for later, which is also very valuable. Industry will often get rid of their obsolete equipment, which for us is far from obsolete. And they'll give you donations, and they'll also help you with fab, like mounting chips. And then they'll help the department by being on an advisory board. They will give student internships. They'll give sometimes fellowships, so it's very useful. And for small companies, you can team up on SBIRs and STTRs. You have to be careful with IP, and I'll finish soon, Jeff. Prepare an NDA before telling a company any technical details. They expect you to do this, so they will think you're a fool if you don't do it. After the NDA is signed, ask the company for as much technical information as you can get. Sometimes this will be very little, but keep pushing, because otherwise you can get surprised. You can start working on something and do things that they already know, and then they kind of think you're not useful, so get the information. Some companies are notorious for just stealing your ideas. Ask around which these companies are. You can ask me offline. I don't want to comment right now. And ask your tech transfer office to submit the disclosure if you feel uncomfortable with the company, just in case. And if you have a contract, request that the IP is negotiated in advance. The company will usually request it, but it's fine if you request it as well. So how do you not dry up if you keep doing this for 30 years like I did? You always write proposals that have preliminary results because you want to be credible. You submit many proposals initially, like John did, because you want feedback. And again, you don't have time later to do all this. Don't promise what you definitely cannot do, but always push your ability a little bit. Be realistic, but ambitious. This is a tough one, actually, to gauge. It's a little individual, I feel. Spend a lot of time learning about your prior work. Reference everybody and their grandmother. I mean, this is super important. For one thing, it's important to do your background work. For second, you don't know who's going to be reviewing this. So you want to make sure you don't offend people by not referencing their work. It's good to write collaborative proposals because you keep learning new things and get new ideas. And also it's just more interesting. Do your homework, expect to spend some time and money in order to get more. And that's just an investment, it's reality. And make sure, should not be forgotten for academics, make sure that your projects are really good theses, because our primary mission is really education, and people that have the money know this, they know, at least the ones that you want to work with. So because proposals need results, student recruiting is completely the key. And every project has the right student. And it's really important to match this. And just like in a company, not everybody is going to work on any task. And so I've been in situations where I can get continued funding for something, but none of my students are interested, and I had to refuse the money. You shouldn't be stingy when recruiting. So budget in your proposals something that can help you recruit. John asked me about this. So RU stipends are really useful for this, and you probably know that already. But you can budget extra travel for conferences just to take students. And I've done justifications in the budget proposals for this, for recruiting. And then I budget supplies, and you know that whenever you wanted to buy something for the lab, it was possible, right? So if you budget extra supplies and tell the students, if you want something, here's money, you can order it, buy it. So these are all things that are good for recruiting in general and keeping your students happy. There's no educate co-advisors so that there's older they expect include students in proposal writing, because not only it's a little slower, you know, but it's really worth it. And also you get a sounding board and reward students with good experiences. And thanks to all of my excellent students, here's a few generations. We went on these field trips, and you'll recognize some of these radio telescopes, Jeff, I think. But John is in a couple of these pictures, right? You're at the VLA and on Mauna Kea.
And Arecibo.
And I went over. It's really hard when you do a slideshow. Thank you for your attention, and any questions?
Great. All right, thank you, Zoya. Questions for Zoya, or in fact, for any of our panel members?
I can stop sharing maybe.
Sure, yeah. So don't be shy. Questions? Anybody?
I'll ask one for Zoya. You have any advice for forming in teams with industry? I mean, it seems to me that, of course, the best solution is that you have a good colleague in that, you know, in industry. That would be good. But if you don't, do you have any thoughts or suggestions on how to go about forming those?
Yeah, sure. So one way to do it is to ask your colleagues who you know. So I'd be happy to do that. Another way is to go to your, so I've done this in the past, you know, people come and ask, or not students, but the companies come and ask for interns. And then you invite them to come to the lab, and you show them what you do and what the students learn, and, you know, spend some time on the classes, but then also show them the research lab. And a lot of times things just kind of flow from there. So those are two that immediately, if I think of others, I'll let you know.
Thanks.
You've probably done that, but sometimes you have to do a lot of tours to get, you know, because all it takes is one person at the company who you can really talk to, right?
All right, other questions?
Oh, there's a question in the chat.
There's a couple of things. Well, there is a question from Yaya in the chat for you, Zoe, I think.
Oh, when do I get time to play tennis? At 5:30 in the morning, Yaya. I'm serious. Yeah, it's a good start of the day. We play tennis when when URSI is in Boulder. This is where the question, very important funding question comes from. Actually, I have won projects on the ski lifts during URSI, just so you know, so don't underestimate the sports. So thank you, Anastasius Papathanasopoulos. Oh, it cut off the end of your name, Sopoulos, probably. You're welcome. I wanted to ask if you could comment on how much should be accomplished before submitting a proposal. Oh, so so my experience is that you definitely have to show some results. Now, how much, of course, depends on the topic, but it would be great if you had at a minimum a conference paper on the topic. And if you can put a plot of something that you've accomplished, or it depends on the nature of your work, or a picture of hardware or even a student working on the hardware, that tends to be essential, I would say. Do you want to maybe give me an example so I can, because how much is, I don't know how to quantify it without an example.
So hello, can you hear me?
Yes, very well, thank you.
So I was thinking, like, sometimes you have to submit a proposal and then you have to promise something. So sometimes people expect you to basically almost have accomplished what you promise, and sometimes just a promise with some preliminary results is enough. And there is no like strict guidelines on how much you should accomplish before submitting the proposal. So sometimes people say this is not enough, and sometimes people say maybe you have already accomplished what you promised.
Yeah, so I would say, a couple of small, what I usually do is I'll have a couple of small publications that show that some peer has evaluated your work and think it's acceptable. It's new and it's acceptable. So that's really what you want to show. And that your theory kind of works. You had this idea and it's doing something in that direction. I don't think that it's good to have everything finished, because after all, people do want to pay you to do something new. I'm not sure how to quantify it. Maybe below 20%, I would say, finished, and 80% roughly. I would think if I analyzed my proposals, that would be about the right ratio. Does that help?
Mm-hmm. Yes, a lot. Thank you so much.
Sure.
Thank you.
So another person has their hand raised, Prabhat?
Hi, can you hear me?
Yes.
Yeah.
Thank you for the great presentations. So I have a question regarding writing a proposal with your advisor, or your former advisor, your PhD advisor. Why is it not a good idea? Because I'm just starting my academic career. So why is it frowned upon that you shouldn't write a proposal with your previous advisor? I think Dr. Chisum had addressed this. I think
It may not be frowned upon. It's just that, so I told John that and all of my students who have become professors, that initially they should establish themselves alone, because you don't want anybody in their organization or at their university telling them, oh, well, your advisor helped you get this.
Mm.
And usually it's the other way around. It's they help you more, right? So that was personally my advice, but maybe John can give you his perspective.
I mean, that's exactly, as Zoya said, she advised me in that direction, and I've gotten that same advice from most of my senior colleagues. It's, and from my experience, so I have not formally worked with Zoya on a program since I worked for her as a graduate student. And I now feel that I've established myself enough to where it would be really fun to work with her. But had I done it too early, I think it would have been dangerous.
I wouldn't have let you.
Yeah, and it just wouldn't have been a good idea. I think part of it too is I found that the things that I thought I was going to pursue as a new faculty member are different than what I ended up pursuing. And had I, say, collaborated with my advisor, it would have kind of stayed in, the same sort of stream that came from her initially. Instead, I branched out and kind of created my own stream, found different collaborators, and now seeing, oh, now we can kind of join those back up and see how they complement. So on a personal level, I think it's way more satisfying to have, branched out on your own. And yeah, strategically, and, for tenure packages and all that, you'd really like to show that this is your work, that you are the primary, developer of ideas. And even if in reality you are the one who developed all the good ideas, it's really difficult for people to believe that if you're collaborating with your former advisor, especially in areas where you used to work with your former advisor.
Thank you. That makes sense. Yeah.
Yeah, I would say my rule is after tenure. After you get tenure. And so John is up for tenure soon, and then we'll write the proposal. We can make those mimics for you if you want, the millimeter wave one. And there is one exception though, and I'll tell you, one of my first PhD students, actually, he was third or fourth, Wayne Ford. He's now a chair at the University of Hawaii. And I actually sent Wayne out with a subcontract. So that's the only exception. And that was to help him get the job because he wanted to go only to one university, which was the University of Hawaii, because that was he was from. And so to maximize his chances, I sent him with a dowry, if you want, he got some initial money. And so we did collaborate a little bit there, but that was really just assistance, if you want. And I think it would be helpful for a lot of people. Sometimes it's not necessary,
Thank you.
Great. Any further questions? We have a few more minutes. Okay. Well, if there are no further questions, I want to thank our panelists again. I really enjoyed this. I hope that all the people that participated, all the young researchers got some useful information that they can take forward in their careers as scientists and engineers at universities and industry and wherever. Hope that the advice is going to make you more successful as grant writers in the future. Keep in mind that this session was all recorded. This will be posted to the Whova platform soon after the session is over. So if you want to come back and look at some of the things that Zoya or John or Anna presented, you can do that. And I'd also appreciate your feedback through, you can use the link to send me a message through Whova if you like, or send me an email using my email address on my profile. I'd love to hear any reaction that any of you have about this tutorial, both positive and negative. And if there are no further questions, thank you all again. And I hope you enjoy the rest of the radio science meeting.